Okay. All right, so good afternoon, lads and ladies. Today I am recording for you the first of 2 lectures that will be pre-recorded while I'm out of town. Let's get to it. Okay. Oh, why is it not connected? No, that's the other one. This one, please. All right, there we go. Okay, so on Monday we talked about linearization, linear approximation, right, which are the same thing. Talked a little bit about differentials. The next few topics for us to cover, there's kind of a disparate mix-a-mash of different things. So let me pull up the syllabus really quick. So we've talked about linear approximation. So the next obvious thing is min-max problems from section 4.1. So certainly we're going to start there today. And then we're going to talk about graphs of f and f prime, L'Hopital's rule, and curve sketching. Now, I don't expect us to fit all of this into this week, especially in this format. But today, in this lecture, I'm going to talk about min-max problems. We're going to talk about graphs of f primed and f and see how they're related. We've done a little bit of this back in section 2.8. And then we may talk about L'Hopital's rule and curve sketching if there's time in the second video, where I may break that up a little bit more. But first, min-max problems. So this is MAC2311, section 004, and the lecture, although I'm recording it Sunday night, is the lecture intended for 21:20. And today, we're talking about minima and maxima, which hopefully are things that you remember from pre-calculus. Of course, these are the concept of a local min or local max, absolute min, absolute max. Those are all addressed as far back as college algebra. But really, the full story has been kept from you until now. So now here in Calc 1, finally, you will get the full story of minima and maxima, which together, by the way, are called extrema. So if I want to refer to the set of all mins and maxes for a given function, I will refer to them as the extrema for that function. First, a definition and a picture. A local min I should just say definition of local min. We say f of x has a local min at x equals a if f of a is less than or equal to f of x for all x near a. And the definition of a local max, we say f of x has a local max at x equals a if f of a is greater than or equal to f of x for all x near a. There's a few things that you might want to ponder about this definition. I know that certainly the word near is a little bit ambiguous, but what we mean is, if there is some open interval centered at a such that f of a is greater than f of x for all x's in that open interval. So the picture here, that's one that surely you've seen before. Right here, I have a local min, because if you look at any little interval centered at a, i.e. you focus your attention on this little window, then that's the smallest the function gets anywhere nearby. So we'd say locally, that is looking nearby, that is a minimum value for that function. On the other hand, over here, I have a local max because if I look at a little open interval centered at A, which corresponds to looking at this kind of open window up here, then that is the tallest point on the graph in that window. So locally, i.e. nearby or within a neighborhood of that point, that is the highest point. So this is a local max, and this down here is a local min. And you may notice that on this particular graph, this is often the case, that at this local min down here, whoop, shit. And at this local max up here, the tangent line is horizontal. This is often the case. It's not always the case. I want to be clear about that. But if your function is nice and smooth, then that will always be the case. Before we get going any further, I need to define for you the other two major objects in this section, and that's an absolute min and an absolute max. So an abs min, I'll call it abs min, short for absolute. We say f of x has an absolute min at x equals a if f of a is less than or equal to f of x, not just for all x near a, but for all x in the domain of f. And similarly, the abs max definition says, we say f of x has an absolute max at x equals a if f of a is greater than or equal to f of x for all x in the domain of f. Okay. So these pictures and definitions should be familiar to you. And then I'll draw another picture corresponding to the concept of an absolute min and an absolute max, but hopefully these aren't totally foreign. Yeah, let's look at that picture. Oh, a note. Of course, since normally when we have these classes, I would pause and ask for questions from time to time. You may want to manually pause the video. That'll give you the opportunity to complete your notes, right? That's one of the things that I know people do when I stop and ask for questions is just catch up writing. And also you may want to star or put little questions next to certain things in your notes that you would like to ask me in office hours or that you would like to ask through email or Canvas messages. Because you cannot stop and ask questions now during this lecture because of course it is pre-recorded. So yeah, that's all. Make sure that you're taking good notes. The fact that this is a pre-recorded lecture rather than a regular class does not mean you don't need to take notes. In fact, it means you need to be even better about taking notes because we're not having a back and forth. And so this won't stick in your brain as well unless you take notes. So please take a second, maybe pause the video right now. Make sure you have these definitions nice and clear in your notes. And then also be sure to include any little marks or stars or asterisks next to things that you would like to ask questions about. And that way you can remember after you've finished watching the video to send me an email or Canvas message with those questions. Or you can pop into one of my office hours this week and ask me a question there. Okay. So what is the difference between an absolute max or min and an local max or min? Well, I'd like to redraw that picture we had there a second ago, but I'm going to redraw it with some some variations. So how about like this? I think we would all agree that right here, right here, and right maybe here, we have local extrema. This would be a local min. This would be a local max. And this would be a local min. Now, there is no absolute max here because these arrows on either side indicate that the graph of the function one second, guys, sorry. Okay, I think we're back, right? Yeah, that should do it. All right, so we said that, yeah, there's a local min here, there's a local max here, and there's another local min here. The local min on the right is a little bit special though, because if you notice, the graph never gets lower than this. It goes up on the left, it goes up on the right, and nowhere does the graph ever attain a value smaller than the y value here. So let's give this y value a name. We call this L. L, and let me call this A. And we'll say that the local min at x equals A is also an absolute min. Right? Because that is the lowest the graph ever goes. So we would say that the function has an absolute min at x equals A here. In addition to saying the local min, and that the absolute min value is L. Now, it's my hope that you guys, in your discussions of these things in previous classes, understood the distinction between the location of the min and the value of the min, or the location of the max and the value of the max. When we talk about locations, like where is something, we're always talking about the x value. And we talk about the value of the min, or what is the min, we're always talking about the y value, or the output. So where is always for what input, and what is always what's the output. In other words, when I ask you where is something, where's the min, where's the max, I'm always asking at what x value is the min, at what x value is the max. And if I ask you what is the min, or what is the max, what is the max value, what is the min value, then I'm looking for the y value. There's an important theorem that I could try to characterize or give you a feel for by, instead of having these guys be arrows, filling them in. So down here we had a local min and also an absolute min. Now by turning both of those arrows into filled in holes, one of them is lower than the other. This guy over here, he just became a local max, and he just became a local max. It might not look like we're used to seeing local maxes look. It's not the top of a hill. But if you put a little window around here, is that filled in hole the highest point anywhere in that window? Yeah, it is. And if I put a little window around here, is that filled in point the highest point in the window? Yeah, it is. And the one on the left is special because he's also an absolute max. So I could say the function has an absolute min at x equals a. And if I call this over here, I don't know, x equals c, then I could say the function has an absolute max at x equals c. And I haven't labeled the max value here, but if the y value up there was, say, m, then we would say, and the max value, the absolute max value is m. Okay. So local mins, local maxes, absolute mins, absolute maxes, they can overlap. Your absolute extrema will always be local extrema also, right? If you are an absolute max, you are also a local max. And if you are an absolute min, you are also a local min. But not every local extremum is an absolute extremum. So there are plenty of local mins and local maxes that are not necessarily absolute. The theorem I was alluding to is every continuous function attains an absolute max and an absolute min. I'll write the min first. An absolute min and an absolute max on a closed bounded interval. So if I take a continuous function and I restrict it to a closed bounded interval, that function will always attain an absolute max and an absolute min. And the picture is really this picture, where instead of having arrows, instead of having the interval of its domain go on and on and on forever, I close the interval. I make it closed and bounded. This is related to a really important concept in analysis called compactness. And if you are curious about that, I strongly encourage you to Google compact set, because it's a really, really big deal in analysis, which is basically big boy calculus. So one of the things that you may encounter in your homework, I might give you a function and a closed bounded interval and ask you to find any local mins, local maxes, absolute mins, and absolute maxes. And there will always be an absolute min and absolute max if I'm restricting to a closed bounded interval. To find these, first, you want to seek out all horizontal asymptotes, well, not asymptotes, I'm sorry. So there's a little bit of stuff I want to cover before I describe how to go about finding these. Let's do that first. So there's some language and some technique stuff that you guys should see before we come back to that. Okay, so finding extrema. First, a little definition. The number C is called a critical number and that's the thing we're defining for f of x, provided one, that C is in the domain of f. All right, got to be in the domain of the original function. 2, that f primed of C is equal to 0, or f primed of C is undefined. These critical numbers it turns out, are places where f can go from being increasing to decreasing, or from decreasing to increasing. They look like, what I mean by look like is like on the graph, you know, maybe you go from being decreasing to increasing in a smooth way. Maybe you go from increasing to decreasing in a smooth way. Maybe you go from decreasing to increasing in a pointy way. All of these things are possible. So I'll label the critical numbers here as C1, C2, and C3. At these two, f primed is equal to 0. You've got a horizontal tangent line there. At this guy, you've got a vertical tangent line. This is a place where f primed is undefined, right? So I'd say f primed of C1, that's 0, because yeah, horizontal tangent line right here. F primed of C2 is also 0. And f primed of C3, this is undefined. I've got a sharp point here, so definitely f is not differentiable, meaning f primed of that x value does not exist. And you'll notice that I've got a local min here, I've got a local max here, and I've got a local min here. And you can have cusps, pointy things that point up also. So you could have a local max coming from an undefined f primed as well. There's something called the first derivative test. This says if f primed goes from negative to positive at x equals c, where c is a critical number, then f of x has a local min at x equals c. You can turn this on its head. If f primed goes from positive to negative at x equals c, then f of x has a local max at x equals c. And I'd like you to think along with me in this picture. So if I'm wandering in from this way towards C1 along the graph of f of x, this here is the graph of the original function f of x. I am decreasing, 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 and then I turn around here and I start increasing, 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 increasing. What that means is that f primed, the derivative is negative, 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 and then I turn around here and f primed is positive, 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 positive. So here at C1, f primed went from negative to positive, which means that f went from decreasing to increasing. We've seen this before, that if f primed is negative, you're decreasing, and if f primed is positive, you're increasing, just to remind you of that. So here where I'm decreasing, 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 this is f prime negative, negative, negative. And so f prime changes sign here. I go through C1 and I go from decreasing to increasing. That means f prime went from negative to positive. And so according to the first derivative test, that means I rolled through a local min. And from the graph, we can see that it was a local min. Similarly at C2, I'm approaching here, increasing, 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 and then I turn around, decreasing, 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 which means f prime went from positive, positive, positive to negative, negative, negative. So at C2, f prime went from positive to negative. And that lines up with what the first derivative test tells us again, that if f prime goes from positive to negative at x equals c, then f has a local max at x equals c. And here we see f prime, because where f is increasing, 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 I know f primed is positive, positive, positive. And then we turn around and f is decreasing, decreasing, decreasing. So f primed is negative, negative, negative. So f primed went from positive to negative, and the original function f rolled through a local max. Even here, where things are pointy and not nice, where f primed is undefined at C3, the same rule works great. F primed here is negative, f primed here is positive. F here is decreasing, right? So f primed is negative. F primed over here is positive because f is increasing. So f prime went from negative, negative, negative to positive, positive, positive. And that indicates that we went through a local min. So if C is a critical number, then you can check and see whether it's a min or a max by making a number line for f primed, kind of like when you learned how to solve rational or polynomial inequalities in pre-calculus by making a number line and building test points. And that's really the big thing that we're learning how to do here. Before I let you go, there's something called the second derivative test that is also important for discussing extrema. And then we'll do an example or two. The second derivative test does the same thing as the first derivative test, just in a different way. So this says if f of x is differentiable at x equals c, and f double primed of x is continuous at x equals c, and f primed of c is 0, then if f prime primed of c is positive, then f of x has a local min at x equals c. And if f prime primed of c is negative, then f of x has a local max at x equals c. So the second derivative test gives you a way of thinking about whether a critical number is a min or a max based on the shape of the graph nearby. And it only works if the function is smooth. It doesn't work for pointy things. But sometimes it's easier than making a number line to calculate a second derivative and to plug c into that second derivative. The reason this works is going to have to wait until I talk to you about concavity, because that's really what the second derivative describes, is concavity. And that's something that connects nicely when we talk about the shapes of f, the graphs of f and f prime, and how it relates to higher derivatives. Basically, I'll show you concavity. If f prime primed of x is positive, then f of x is concave up. And if f prime primed of x is negative, then f of x is concave down. concave up stuff holds water. Concave down stuff, water would run off the back. So if you have a critical number at a place where you are concave down, i.e. if f double primed is negative, then that's going to be a local max. And if you have a critical number at a place where you're concave up, then that's going to be a local min. So the second derivative test can be visualized this way. Okay, let's look at one or two examples, and then we'll see if there's time to talk a little bit about some of these other things. They may have to wait. Okay, applications. Minimum and maxima, so definitions. This is good. Extreme value theorem, we talked about this. Okay, looks like they don't have the second derivative test. They might save that for a little later. So let's look at one of these guys. Something hopefully not boring. Find critical numbers, find mins and maxes. All right. Yeah, so before we dive in and do this, let me go ahead and describe that closed interval method. So I told you at the start of the video, or a little bit while ago, that any continuous function on a closed bounded interval attains a min and a max. So finding all mins and maxes for a function continuous on the closed bounded interval a to b. Okay, your book calls this the closed interval method. 1, find all the critical numbers. That means calculate f primed of x, find where f primed of x is 0 or undefined. 2, you want to identify, so you use the first derivative test. You could use the second derivative test also. To determine whether you have local mins or maxes, or neither at those critical numbers. And then third, you want to compare the y values at the mins and maxes with f of a and f of b, the y values at the endpoints. So your absolute min or absolute max may come from the y values at the endpoints. All right, so this is the procedure for finding all the mins and maxes, including absolute mins and maxes, for a continuous function on a closed bounded interval. First, you calculate the derivative and figure out anywhere the derivative is 0 or undefined. Those are the critical numbers. Then you use either the first or second derivative test to identify mins and maxes, right? So like, okay, these critical numbers were mins, those critical numbers were maxes. Then you calculate the y values at all of those mins and maxes. You also calculate the y values at the endpoints of your interval. Then you compare all those y values. The largest one, that's your absolute max. The smallest one, that's your absolute min. Let's do it for one of these functions, and then I'll end the video because I think we're getting about to the right length here. Uh, 48. 49 is red here. That means it's a little extra good. So let's write that down. We want to find all mins and maxes for f of x equals 2x cubed minus 3x squared minus 12x plus 1 on the closed bounded interval -2 to 3. So I'm going to find all the local mins and all the local maxes, and any absolute mins or absolute maxes. First, I need to find the critical numbers. So I calculate f primed. That's going to be 6x squared minus 6x minus 12. The 1 differentiates to 0. I can factor a 6. I get x squared minus x minus 2. And then I want to try and factor this so I can figure out where it's equal to 0. That's 6 times x minus 2 times x plus 1. So my critical numbers are, so f of x has critical numbers. F primed here is never undefined, it's a polynomial, but it is equal to 0 at x equals -1 and at x equals +2, right? This factor is 0 when x is -1. This factor is 0 when x is +2. So those are my critical numbers. Now I'm going to use the first derivative test here, and the easiest way to do this is to draw a number line for f primed. I plot those critical numbers. And remember, my goal is to say whether f prime goes from positive to negative. So this is this test point thing that you should remember from pre-calculus. I'm trying to solve the inequality f primed of x is greater than 0, or f primed of x is less than 0. In between -1 and 2, in this region here, I can test x equals 0 itself. And if I plug in 0 for x in f primed, I discover that f primed of 0 is -12, which is certainly negative. If I test something to the left of -1, like -3, I'll find that f primed over there is positive. And if I were to test something to the right of 2, like +3, I'll find f primed there is positive as well. And you may remember there are some tricks having to do with multiplicities that will allow you to do that bit faster. In any case, I know that f is increasing here, f is decreasing here, and f is increasing here. Because f primed is positive, f is increasing. F primed is negative, f is decreasing. F prime is positive, f is increasing. So I'm going up, 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 down, on, down, up, up, up. That means that I have a local max at x equals -1 and a local min at x equals +2. The max value at x equals -1, to find that, I need to plug -1 into f of x, the original function. Now that's going to be 2 times -1 cubed minus 3 times -1 squared minus 12 times -1 plus 1. This is -2 minus 3 plus 12 plus 1. That's -5 plus 13, which is +8. The min value at x equals 2 is f of 2. And this is going to be a little harder to compute. That's 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 1. That's 16, 2 times 8 minus 12 minus 24 plus 1. So 16 minus 12, that's +4. Minus 24, that's -20. -20 plus 1 is -19. So far, I know that I have a local max at the point -1, 8. I know I have a local min at x equals 2 at the point 2, -19. And one of these or both of these might be absolute maxes or absolute mins. This local max might be the absolute max. This local min might be the absolute min, but I need to check the endpoints. So f of -2, the left endpoint, zoom out a little so you can see it. F of -2 is 2 times -2 cubed minus 3 times -2 squared minus 12 times -2 plus 1. That's 2 times -8, that's -16, minus 3 times +4, that's still minus 12. Minus 12 times -2, that's plus 24 plus 1. So what does this come out to? -12 and +24, that's +12. +12 and -16, that's -4. -4 plus 1 is -3. Okay. So -3, that's not the lowest the function ever gets, that's for sure, because I know I go all the way down to -19. It's also not the highest the function ever gets, because I know I go all the way up to 8. So there's no absolute extrema coming from the endpoint x equals 2, -2. At the endpoint x equals 3, f of 3 is 2 times 3 cubed minus 3 times 3 squared minus 12 times 3 plus 1. What is that? That's 2 times 27. That's 54. Minus 3 times 3 squared, that's minus 27. Minus 12 times 3, that's minus 36 plus 1. What is that? 54 minus 27. Well, 50 minus 25 would be 25. 54 minus 25 would be 29. Minus another 2 is 27. Oh, yeah, of course it is. Yeah, so this is 27. Positive 27 minus 36. So that is -9. -9 plus 1 is -8. Okay, so here, the endpoints are not bigger than either of these and not smaller than either of these. The local min at x equals 2 has y value -19, which is smaller than the smallest of these. And the local max at -1 had y value +8, which is larger than the largest of these. So this function's absolute max is 8, and that's attained when x equals -1. the absolute min is -19. And that's attained when x equals +2. And there are no other extrema. This absolute max, of course, is also a local max. This absolute min, of course, is also a local min. But that's it. That's the game. So this is where I'm going to end this video talking about mins and maxes. You now know the whole game for finding mins and maxes. We will play a little bit more with these things in the future. The topics that I also want to cover this week, of course, Monday we're going to talk about linear approximation, and I'll do my best to introduce the min-max problems gently there. We'll also maybe talk a little bit about graphs of f and f prime. Other things to talk about this week are L'Hopital's rule and curve sketching. This curve sketching section requires a little bit of love, so I do want to make sure we do something there. It is getting late though on Sunday night, and so I'm not sure I will record any more of these for now, but I will do my best to get everybody good resources, hopefully a nice video lecture for at least section 4.5. And then the other things I will address, or from your perspective, have already addressed on Monday, because you won't be seeing this video until after that. All right, I hope you guys have a lovely rest of your day. Remember, if you have questions based on these notes on this lecture, please don't hesitate to reach out to me. Even though I am out of town, I am doing office hours, still answering emails, all of that normal stuff. The only difference is I don't have the materials or physical things like the document camera where I am to do the lectures. So those are pre-recorded. So please continue working, treat it like a normal week. It is a normal week. And if you have questions, comments, concerns, reach out to me through all the normal channels, Canvas, email, or office hours. All right, take care, guys.